In this next section, we want to look at some different types of integrals that involve trig functions. To be exact, we want to look at the integral of a power of sine of x times a power of cosine x, a power of tangent x times a power of secant x, and then we have three different types where we have sine of a multiple of x times some other multiple of x, sine of a multiple of x times cosine of a multiple of x, and the product of two cosine functions, each one of which is evaluated at some multiple of x. For the integrals involving sine of x and cosine of x, we'll have three trig identities that we'll need to know. One of them is the familiar cosine squared plus sine squared equals 1. The second one, if you remember from pre-calculus, cosine squared of x is 1 plus cosine of 2x over 2, and sine squared of x is 1 minus cosine 2x over 2. In these two formulas in the middle, you want to understand that this says cosine squared of something is given by this formula where you evaluate the cosine at 2 times the something. The letter x is just a bookmark here. Also, 1 plus tangent squared of x equals secant squared of x will be useful for us. For integrals that involve powers of sine x times powers of cosine x, the easiest case is when one of the two powers is an odd positive whole number. For example, in the integral sine x cubed of x times cosine squared of x with respect to x, the 3 is important to us. When you have such power, split one of the factors off so that you have only sine squared x cosine squared left, and write the sine of x down beside the dx. The reason that you do this is when you had the odd power on sine x, when you split off a factor, an even power is left. And because we have this trig identity involving sine squared and cosine squared, we can make life simpler for ourselves. So instead of writing the integral as this, we'll take this sine squared of x and write it as 1 minus cosine squared of x times cosine squared x times sine of x dx. If you let u equal cosine theta, then du is negative sine x dx. You can think of the minus sign as being multiplication by negative 1. Sine of x dx is negative 1 times du. It's the negative of du. And the reason I wanted to write it this way is in my integral, I literally have sine of x dx. If I rewrite my integral in terms of these new quantities, it becomes easy. It's the integral of 1 minus u squared times negative 1 du. After you do a little algebra to simplify the thing, it's integral u to the 4th power minus u squared with respect to u, which is a polynomial, which is easy to integrate. Then you put back in that u was cosine x, and your antiderivative is given by this formula. So an odd whole number positive power on one of the two functions is a good sign. It's not necessary that both powers even be whole numbers or positive. 1 over square root sine x, for example, is x raised to the negative 1/2 power. The thing that's important to me, though, is the 3. I've got 3 factors of cosine, so pull one of them off to the side and put it with the dx. Write cosine squared of x as 1 minus sine squared of x. Simplify the fraction. Let u equal sine x so that du ends up being cosine x dx, which is that part there. This turns it into an integral that is not a polynomial, but at least is just constant powers of the variable. So this then is easy to do also. If both of the powers on the sine x and cosine x are even whole numbers and not negative, which includes 0, then we're going to use these two identities. For example, the integral of cosine squared of x dx is the integral of, use the trig identity to rewrite cosine squared of x as 1/2 times 1 plus cosine 2x. Pull the factor of 1/2 out front. An antiderivative for 1 is x, and an antiderivative for cosine 2x is 1/2 sine 2x. Then add your constant of integration, and you have your antiderivative. Or, if you want to look at the integral of cosine squared of x times sine squared of x, you'll reduce both of the squares using the trig identities. You've got two factors of 1/2, so combine them and pull it out of the integral. 1 plus something multiplied by 1 minus something is 1 squared minus the something squared. Once you have cosine squared of something again, though, that's 1/2 times 1 plus cosine of 2 times 2x. Then you can combine like terms. The antiderivative of 1/8 times the integral 1 minus cosine 4x dx is 1/8 times x minus 1/4 times sine of 4x. Add the constant of integration. This isn't as nice as the odd power thing, though. For integrals that involve powers of tangent times powers of secant, the easiest case is when the secant is even and positive. The reason for that is this. You can remove two factors of secant x and put it with the dx. What's left has even powers of secant and maybe some tangent factors. Even powers of secant can be reduced down into tangents. So you've got something that has tangents in it multiplied by secant squared of x dx. And then obviously you're going to make a u substitution because the derivative of tangent x is secant squared x. For example, look at integral tangent to the fourth power x secant to the fourth power x with respect to x. Split off a secant squared and put it with the dx. This remaining secant squared here, because of our trig identities, is 1 plus tangent squared. The obvious u substitution is u equals tangent x, and doing the usual substitution business, our integral turns into this, which after you multiply things together, turns out to be a polynomial. The antiderivative is 1/7 u to the 7 plus 1/5 u to the 5th plus a constant, and then put in the fact that u is tangent of theta, and you're done. On the other hand, if the power on the tangent is an odd positive number, then split off a factor of tangent x secant x. The reason we're doing this is the derivative of secant is tangent secant. If I took one factor away from an odd number of tangent factors, I've got an even number left. And I can use my trig identities to reduce the whole problem down into secants with a factor of secant x tangent x dx at the end. For example, the integral of tangent cubed x secant cubed x dx. The power on the tangent is an odd positive whole number, so I split a tangent x secant x away, leaving me with tangent squared x secant squared x. As we said, tangent squared is secant squared minus 1. So I'll have secant squared minus 1 times secant squared times tangent x secant x dx. And although this looks kind of horrible, if you look at u equals secant x, the derivative of u would be secant x tangent x. Du would be tangent x times secant x times dx, which is this bit at the end here. So instead of writing tangent x secant x dx, in the new version of the integral, I'll just write down du because that's what it's equal to. The rest of it, since u equals secant theta, becomes u squared minus 1 times u squared. And by this stage of the game, everyone should agree that that's an easy integral to do. You put back in what u was, in this case it was secant x, and you found your antiderivative. This can work even if there's no secants in the integral. If you look at the integral of tangent to the 5th power dx, 5 is an odd positive number, so I'm going to split a tangent secant off. You might object there wasn't any secant in the problem to start with, but that's okay. I'll just write a secant of x on the bottom of the fraction and cancel it out with the one that I put in, and this integral is still the integral of tangent to the 5th. Tangent to the 4th is the square of tangent squared of x. Tangent squared of x is secant squared of x minus 1. So if you just multiply that out, you'll find that the tangent to the 4th can be written as secant to the 4th minus 2 secant squared plus 1. I'm dividing by secant of x, and I have tangent x secant x dx at the end. Because of the way we add fractions, I can split this part up into 3 pieces. Secant to the 4th over secant, which is secant cubed, minus 2 times secant squared of x over secant x, which is secant x, plus 1 over secant x. And I still have my tangent x secant x at the end. Obviously, I'll use a u substitution with u equals secant x. Having gone through all the substitutions, the remaining integral is easy, and when the dust finally settles, you find that your antiderivative is 1/4 secant to the 4th x minus secant squared x plus the natural log of the absolute value of secant of x plus a constant. If there are no secant factors and the power on the tangent is even and positive, then the suggestion is to repeatedly use the identity 1 plus tangent squared equals secant squared to reduce things down into things that you can do. For example, integral of tangent to the 4th power. Think of that tangent to the 4th power as secant squared of x times secant squared of x. Oh, pardon me, tangent squared of x times tangent squared of x. Convert one of them into secants by writing it as secant squared of x minus 1. Then you're going to have the integral of tangent squared times secant squared with respect to x minus integral tangent squared times 1 with respect to x. And this part is going to be really easy to do because the derivative of tangent is secant squared. This one we're not so familiar with, but we can get it anyway by using tangent squared equals secant squared minus 1 again. So if I split all this stuff up, it's integral tangent squared x secant squared x dx, which we can easily do with a substitution, minus integral secant squared of x dx, which is on our list of things that we know antiderivatives for, plus an antiderivative for the constant function 1, which is easy. I'll leave the details of the u substitution on that first one for the interested listener because, as I said, it's easy. Your answer ends up being 1/3 tangent cubed x minus tangent x plus a constant. If you have an integral of a power of secant and the power is odd and positive, the textbook says we should try integration by parts. So I want to calculate the integral of secant cubed of x with respect to x. As always with parts, you've got a vast number of ways you could rearrange things, but I want to take advantage of the behavior of the trig functions. I'm going to write this as secant of x multiplied by secant squared x dx. I'll call u secant of x, and I'll call dv secant squared of x dx. du dx is secant x tangent x, so du is going to be secant x tangent x dx. On the other hand, dv is secant squared of x dx. That means that v must be an antiderivative for secant squared x, which is tangent x. And then we're going to write down our integration by parts formula, secant x tangent x, u times v, minus integral of v du. V is tangent of x, and when I multiply that by secant tangent x, I get secant x tangent squared x dx. We're going to take the tangent squared and write it as secant squared minus 1. So this line is the same as the preceding one, except that we've done that. Secant of x times secant squared of x is secant cubed of x. Secant of x times 1 is secant of x. So the last part of the integral can be written this way. So the thing that I'm looking for, the antiderivative of secant cubed, is secant of x times tangent of x minus the integral of secant cubed x dx, and minus is plus integral of secant x dx. And at first glance, it looks like some sort of disaster has happened because it looks for a moment like I need to know the integral of secant cubed in order to figure out the integral of secant cubed, which would be bad, but that's not the case. Add this term to both sides, and you get 2 times the integral of secant cubed is secant x tangent x. This has been moved over to the other side of the equation. The secant is on our list of things we know an antiderivative for. The antiderivative for secant x is natural log absolute value secant x plus tangent x. Once I've got it written that way, divide through by the 2, and you'll have one antiderivative. Then you get all the rest of them by adding the constant of integration. And lastly for this section, if you have sine of a multiple of x times sine of some other multiple of x, or possibly sine times cosine, or cosine times cosine, there are trig identities that will allow us to combine these things into not a product of trig functions, but a sum or difference of trig functions. If you look in the textbook, you should see these formulas listed. For example, if I want to calculate the integral of sine of 5x multiplied by cosine of 3x dx, I'm going to use the formula in the middle that we were just looking at. I'm just rewriting the integrand using one of these trig identities. 5 minus 3 is 2, 5 plus 3 is 8. So I end up with 1/2 times the integral sine 2x plus sine 8x dx. The antiderivatives of both terms are easy to get. And after doing the simplification, my antiderivative is negative 1/4 cosine 2x minus 1/16 cosine 8x plus a constant. If you try all of these techniques and none of them works, your book suggests finally reducing everything down to sines and cosines and seeing if you can't do something with that. By the time you start down that road, usually it's beginning to look not so good that you'll be able to get an antiderivative in some nice form. And we'll have to think about other techniques instead of trigonometric integrals. In the next section, we're going to look at various types of integrals that you can do a substitution on and turn into integrals of the type we've been talking about here, and then hopefully use the techniques that we've just mentioned in order to actually do those integrals. We will see about that in the next meeting.